Basically, we've got two large wood storage piles, one being an automatic stacker reclaimer. I'll talk a little bit about that further along. A manual pile here that is formed by front-end loaders. You'll see our boiler building. Top of the height here is 180 feet. The top of our stack is 230 feet. We have a wet cooling tower right here. The whole footprint that we will be taking up is about 60 acres or so. We're on a 131-acre parcel. There was a fair amount of wetlands that we had to work around, and we actually did a really good job of working with our consultants and our engineers to make sure that we were impacting less than half an acre of wetlands, which is a very big deal in this country and especially in Florida. We're located within the city bounds of Gainesville, but we are about 8 miles northwest of downtown. Our facility will generate 100 megawatts net to the grid. On a gross standpoint, we are about 116 megawatts. We use about 15 to 16 megawatts internally. We can power about 70,000 homes with that. We didn't talk about it, but one of the advantages that biomass energy has, which I'm sure you're all aware of, is over other renewables, is it's a baseload technology. Okay, it's available when we need it. You know, if the wind is not blowing or the sun is not shining, we can still generate electricity. Okay, I think you've already seen this photo right here, but again, the existing coal facility, the photo that I was talking about was taken from the top of this boiler over here, looking in this direction up at our site. Okay, the total site that this sits on is about 1,000 acres, and we'll be taking up about 131 acres right in this area right here. It's a little hard to see this, but this is a close-up schematic. We've got the automatic pile right here. We have the manual pile, and then the boiler island is right over here. Okay. Our technology, it's a bubbling fluidized bed boiler. Okay. We will be using selective catalytic reduction to control the NOx emissions. On our Texas facility, we had instituted a SNCR, selective non-catalytic reduction. Okay, but as we were working through the permitting of this facility, the regulators have required us to have more stringent controls, so it necessitated the need of a selective catalytic reduction to take care of the NOx emissions. And then we'll basically utilize our bubbling fluidized bed boiler to generate steam, which will turn a traditional steam turbine generator set. Talking about why we chose this technology. We were looking for a unit which had high availability, high efficiency, and was dispatchable. Okay? A lot of times when you're talking about a solid fuel boiler, they run very well when you run them 24 hours a day, 7 days a week. They have difficulties when you're taking them up and down. The main three boilers that we took a look at, we looked at a stoker, which was a traditional technology that had been utilized, a great technology. We looked at a bubbling fluidized bed, and we looked at a circulating fluidized bed. You may have heard of some gasification technologies. We have not pursued those very heavily, although we've started taking a look at them now, thinking that they may be something in the future. From what we can tell in the research that we've conducted to date, they still are not really commercially available yet. People may say that they are, but we have not really seen that at this point yet. So these were the three main boilers that we took a look at. Why did we choose to go with a fluidized bed versus going with a stoker technology? A couple of main reasons, but I'm going to hit on 3 points. High efficiency was the first one. Okay. We also wanted a boiler that had great fuel flexibility. Okay. The boiler that we're using can burn a wide range of material, both in terms of BTU content as well as moisture content. Okay. The stoker grate can handle a variability, but not quite the same as a fluidized bed. And then the final reason was high reliability. Okay. With stoker grates, sometimes you can have a fixed grate, which is difficult because then it needs a lot of O&M, maintenance. Or you can have a traveling grate, but then you have moving parts in a combustion area, which is probably not a great thing when you're looking at trying to have a high availability and high reliability. Okay. Taking a look at, on your y-axis here, you're going to be able to see heating value of the fuel. okay, versus percentage of volatiles. So up here we've got our coals, moving down the spectrum to our wood fuels over here. Taking a look at it, the technology that had a better use when you have a higher heating value, lower volatiles, was going to be the circulating fluidized bed. When you're talking about lower heating value and higher volatiles, really led you to want to think about a bubble and fluidized bed. It's important to point out that folks are using both technologies for biomass, but this was one of the factors that played into it, was what the main fuel that we were going to be using for our technology. Nice schematic of the boiler itself. Okay, just to point out a couple of the parts right here. We've got the boiler fuel bins, okay, about 45 minutes worth of fuel in these right here, in these bins. On site, in our 2 piles that we have, we're going to have about 15 to 20 days of inventory, okay, which is a decent amount. We'd like to have a little bit more, but that probably is a safe amount in terms of wood storage and what we can actually get, you know, into the site. All of the fuel coming into our facility will be processed already, meaning it will be chipped or ground. We will not be receiving any whole trees or brush or limbs. It'll all be processed before it comes onto our site. We're not utilizing any pellets in our operations. Not that we wouldn't like to, it's just really expensive, okay? I know that in parts of Europe and in the UK they're looking at utilizing pellets for a similar type of technology, but for ourselves we'll basically be using a chipped or a ground material. All clean woody biomass. And Al's going to talk about fuels in more detail later on. You've got the main combustion chamber right here, our fluidized bed. Okay, we've got the chamber floor, the fluidized bed in this area. Primary air is blowing up underneath, and the combustion air that's being fired underneath the bed is what is basically taking the solid state and turning it into a fluidized state. Okay, and the bed material is a sand-like material. The fuel enters from in here from the bins, okay, and enters the chamber above the bed, and then is combusted in the bed. The main reason with the bed is that you're getting a very complete burn, very efficient, less particles going up into the upper part of the boiler up here. There's also overfire secondary air here, and it doesn't show up the tertiary air up here, okay? And then utilizing to control the NOx emissions, we don't show it in this picture, but in SCRs, we talked about selective catalytic reduction. To control the particulate emissions, we're utilizing the baghouse, okay? You could also use something like a precipitator, electrostatic precipitator, but for our technology, we're utilizing a baghouse here. Talking about some of the special features for biomass firing. Again, the fuel storage coming in. This is what the hydro beam floor looks like. So what happens is that the bed material settles there. When the air comes on, it now is about 6 to 8 feet suspended above that floor. Fine ash drops down. You'll have coarse material, that is what we call our bottom ash, and that really is a lot of the involatiles that are not combusting. Okay, if there's any metal that might be in there, if there's any rocks or large materials like that, the fly ash actually goes through the boiler and then kind of comes out in a different area. A very small percentage of ash, about 1% of the fuel that will burn. And again, just a little bit more of a close-up here. We're looking at the bed, primary air blowing from underneath, secondary air, tertiary air. The furnace load burners, we use a small bit of either natural gas or propane to bring the boiler up to temperature. From a cold start, it takes about 14 hours to get the bed up to full temperature, okay? We can hit 70% load, okay, at about 8-9 hours or so, but then full load is up to about 14 hours. From a hot start, if it was just down for a little while, you can come back up fairly quickly. One of the points that we talked about is that GRU, as the off-taker, the utility buying our electricity, they have dispatch rights. So they have the ability to run us anywhere between 100% load and 70% load, okay, at any point that they want, depending on what their demand is. Below 70%, we can operate between 70% and 50%. We have a difficult time making our air emissions, okay? We need to be at a certain level so that we can control the emissions at the point, okay? But basically, at any point that GRU chooses, They have the ability to run us between 70% load and 100% load. They also have the ability, depending on the need, to take us offline completely. Okay, and that's also in the power contract. Okay, the way that we've dealt with that from a pricing mechanism is that we receive a certain amount of revenue if we are available to operate, but GRU chooses not to dispatch us. Okay, it's basically enough for us to pay our fixed costs. Okay, and then as we're operating, we have variable expenses that cover us as we operate. The GRU, it's worth talking about. GRU has run a dispatch analysis, and it's actually shown that we will probably be one of their cheaper units to dispatch once we are up and running. We have on site, we have 3 full truck dumpers right here. It's a very neat process to see when you see this big a piece of equipment, being lifted up. We have 3 of these. We can handle upwards of between 18 and 24 trucks per hour on all 3, running at one time, so quite a bit of fuel. Again, we need about 1 million green tons of material a year. We're expecting to receive material 6 days a week for about 15 hours a day. On Saturday, it may be a shorter time schedule, but that's about average. Okay, the automatic stacker reclaimer. These are pretty neat pieces of equipment. I had the opportunity to go check one out recently at a pulp and paper mill. And what you'll see is that basically material is coming in on an upper conveyor right here, and it's being deposited in a pile in a conical shape on this arm. And this arm can rotate all the way around over here and form this pile. At the same time that you're building the pile, you can also be reclaiming it with this drag arm. Okay? And it has a chain on it that basically just sits down on the pile and eats away on the pile. And you'll notice right here, there's a lower conveyor which reclaims the material, and this is where it goes from here and feeds along the conveyor into the boiler. Ed's already spoken a little bit about this. It's a 30-year agreement. For financing purposes, as an independent power producer, which is what our company is, we don't have any customers ourselves that we provide. We sell electricity to utilities that have ratepayers and customers. You need about a minimum of about a 20-year power contract. Our project in East Texas that we developed had a 20-year agreement with another municipal utility similar to GRU called Austin Energy. That provides energy to the city of Austin, Texas. That was a 20-year agreement. This is a 30-year agreement. We sell all of the output to GRU. So everything that we produce from this facility will go directly to GRU. And that includes all of the attributes such as electricity, kilowatt hours, also capacity, which is the ability to have generation standing by and able to operate if necessary. And then, as Ed mentioned, all the environmental attributes also flow to GRU. And that would be things like renewable energy credits, carbon credits if those develop in the future. Al will talk a little bit, and Ed already has, about the minimum sustainability standards and the forest stewardship program. So I'm going to hand it back over to Al right now. And we can also take questions. And as I mentioned, I'm not an engineer. I've learned a lot about this technology through the process, but we do have one of our lead engineers on the phone, and we can try and answer any questions that you have. The main plan is that we will operate the manual pile. The manual pile basically just forms a pile like this, and then yellow equipment, bulldozers, front-end loaders, form that pile, okay, and put that into about a 35-foot pile that's managed manually. This pile can be upwards of 85 feet, so we're talking a very large pile. We'll operate the manual pile during the day, okay, and then at nights and on the weekends, when we have a reduced stack, you'll be operating your automatic pile.